This example of flux and how we can use it is going to show us another way of which we can solve for the EMF produced by a changing flux. So Faraday's law talks about that when the flux change, the rate of which that change is going to be equal to the EMF which is produced within a loop or in a coil. What we can look at is this question number 9, where now we have a little bit different of a scenario where we have a bar which is a conductor, which only this part of this loop is moving. It's increasing the total area that is being experienced to this magnetic field here. And so what we can look at then is how we can adjust this equation here for the EMF to better utilize some of the variables that are going to be used here. So we know that a change in flux is going to equal, in this case, a constant magnetic field times a change in area divided by time. Now, if we can understand how is this area changing, we can see that what is changing is this length is staying constant. So area obviously is length times width. Our length is staying constant, but it's our width of this area which is increasing as this bar moves from here to here. And this is that change in area that's actually being produced right here. So what we can say is this becomes B times L velocity times time all over time. And we can say that because this right here, remember, distance equals velocity times time when it's moving in a constant velocity. In this case, we have a constant velocity, so this length here is my velocity times the time which was produced. The area which is changing is this area right here. So to find the area of this rectangle which it's produced, we're going to take the length of this side, which is L, and multiply it by the length of this side, which is D, or velocity times time. So we can change our change in area, or we can rewrite our change in area as length times the distance which that went, which was velocity times time. Now, when we do that, we can see that my times actually can go away, and I can rewrite my equation for the EMF as simply B, my magnetic field, length times the velocity, which that bar, so the velocity that this bar right here is traveling to the right. Okay, and that's going to be a very useful equation for us for this type of scenario. So if we look at question 9, it says the moving rod is 12 centimeters long, and it's pulled at a speed of 18 centimeters per second. The magnitude of our magnetic field is 0.8, and so what we want to do first is we want to calculate the EMF and then also figure out the electric field felt by the electrons in the rod. So how we're going to go about doing that. The first thing that we're going to do is to find our EMF. We're going to simply use the equation that we just developed. So our EMF is going to equal our magnetic field, which is 0.8, times our length, which is 12 centimeters or 0.12 meters, times our velocity, which is 0.18 meters per second. So again, we have to convert that to meters per second. When we do, we get a value of 0.0173 volts. Okay? There's a dot right there. So now, as we're working through this problem again, we need to understand which direction is current flowing. Is current flowing in this direction or this direction? So what we can say is that our flux is increasing, and it's increasing because our area is getting bigger. So that means that the B induced has to be opposite B. So B induced would point into the page, whereas B that is there is pointing out of the page. So I'm going to take my right hand, I'm going to put my thumb into the page, and I'm going to see that the current is going to flow around my circuit in a clockwise direction. Okay, so remember, that is the current. Now, I like what this diagram does. This diagram shows electrons. Remember, it's actually electrons that are moving, okay? But remember, current is the opposite of the way that electrons are moving. So we can also figure this out by simply using the right-hand rule or the left-hand rule because it's an electron, right? If we point our fingers out of the page and we point our thumb in the direction of this green arrow, so our fingers are pointing up out of the page, our thumb is pointing to the right of this green arrow, then our force is going to be pointing towards the top of the page. This is the force that's on the direct electron. So if the electron has a force in that direction, then our current would be flowing in that direction. So it's flowing in that opposite direction. For the second part of the problem, we simply need to find the electric field E felt by the electrons in the rod. So how we can do that, there's a few different ways. One way we could do that is we could look at simply the equation for electric field, which is force over charge. So the electric field, we already said that there is some force pushing up on these electrons, right? And so what we would assume is that there is going to be, that's a magnetic force, which is producing that. And so we can say that the force that's really pushing them upwards would be QVB divided by Q. What we can do then is we can cancel out Q, and we get that electric field is going to simply equal velocity times my magnetic field. That becomes 0.18 times 0.8, and we get an electric field of 0.144 for its value. Another way that we can look at this is we can look at, what is electric field, right? Remember, electric field is K Q Q over R squared, and voltage is K Q Q over R. And so if we take voltage and we multiply it by 1 over R, we get electric field. Okay? So what we can do is we can say that our electric field is our voltage divided by, basically, in this case, it's L, or the distance of our rod. So we solved for our voltage by finding our EMF. And so that's that 0.0173 divided by our length, which is 0.12. And again, we're going to get a electric field of 0.144, and this would be volts per meter, right, which is going to produce that same value. So both of those would work. This might be a little bit more technical of how we should solve for it, but both of those are going to work as well.